Thank you. Hey. Hello, everyone. My name is Joanna Regal from KMJ Consulting, and on behalf of the Eastern Transportation Coalition, we're welcoming you to the web meeting today, Hurricane Traffic Volumes Pilot Results. We're going to hear about state experience with real-time connected vehicle data. I just want to go through a couple very brief housekeeping items. If you're having any issues with the audio, you can press *0. If you're having issues with the audio or with the web, please reach out to Justin, 484-557-7009, and he will help you. This web meeting is being recorded. And just to let you know that the presentation, as well as a link to the web, to this recording and a Q&A summary, will be posted on the Coalition's website. Anyone who registered or participated in today's event will receive a follow-up mailer with links to those items. Since our participants are muted, we are asking that you use the chat box for your questions. If you can simply type them in, Stan will stop throughout the presentation, and we will work on getting those answers to you, and they will all be included in that question and answer summary. This time, I'd like to turn it over to Denise Marco. She is the TSMO Program Director at the Eastern Transportation Coalition. Denise?
Thank you, Joanna. Can you hear me?
Yes, you're clear.
Super, thank you. Welcome, everyone. Good afternoon. We have a lot of some great information for you today with quite a few speakers, so I will be brief. I'm just really thankful that we've had the opportunity to put together this pilot. I know that sometimes when I talk with states and I talk with people, everybody says, oh gosh, I'd love to see connected vehicle data. I'd love to work with connected vehicle data, and I think you'll see what we've done, some of the details that are, the devil's always in the details, and hopefully it will bring you a little bit further, a better understanding of some of the challenges that connected vehicle data, as well as some of the rewards. So with that being said, this is our agenda for today. I'm going to introduce, welcome, and then I'm going to turn this over to Stan Young, who is from the National Renewable Energy Lab. He is our resident data scientist for the coalition. He's going to weave back and forth through the speakers that you see on the screen. He's going to start and tell about the 4 goals and objectives that this pilot started with and what we were working towards. He's then going to hand it off to Jaap, Hoek, who is the Director of Solutions Engineering for Wejo, who's going to tell you a little bit about the data itself, the Wejo data that we used, and some of the vast amounts of data that we used. He's going to turn it back turn it back to Kaveh Sadabadi, who is a senior faculty specialist over at the University of CATT Lab, who talked about how he worked on looking at how the volume data is accurate, the accuracy of the real-time data. Stan's going to finish up with some goals, some objectives. We are going to take a dive into some of the state feedback. We're going to have Simona from VDOT come in and talk about a little bit about some of the users and the methodologies we used, which were a little bit unique in this pilot, and then back to Stan for the lessons learned and summary findings. So we have 208 folks registered today, 26 states, because we did open this up, because we did get quite a few requests from states outside the coalition. So as you can see on the bottom, we've got a wide variety of DOTs, universities, MPOs who are signed up and on the line right now. The coalition, this is the update that we always provide every single webinar of some of the recent events we've had, some of the upcoming events. We did have a travel information roundtable where the states got together and talked about what they're doing relative to travel information within each of their states. We are in the process right now, I think you know, of rewriting an RFP for our traffic data marketplace, which is now called VPP, which will be called TDM. So we are in the process of working through that. And then we had a webinar back in December on optimal traffic monitoring to talk about many of the ways that you can look at traffic monitoring via sensors or technologies. Upcoming, we have a RITIS user group meeting in February. We have a Waze technical working group. We have 2 workshops. We are working directly with Waze product team. The coalition is on how to enhance some of the Waze app. And then we have a Travel Info Virtual Summit that's coming up in April, innovative capture and dissemination of travel information data. So again, a lot going on. Never a dull moment around here, but that's what we got going on. So With that being said, I'm going to turn this over to Stan. Stan, I'd like you to do the introductions. This is a team you worked with. You guys did a lot of great work. So let me bridge this over to you right now. Are you there?
Yes, I'm here, Denise. Thank you. Thank you. There are a lot of people who put in a lot of effort on short notice to make this proof of concept, to make it work. You're going to hear from three of us, or a little more than three of us today, myself, Jaap, and Kaveh, but a lot of work behind the scenes by Zach, Peter, Aymar, and his team. So I want to acknowledge all of them. We're going to try to bring it up to the very top level and not get lost in all the details of what we had to tackle to get this done in a short time frame, and give you an overview of what we attempted to accomplish. I am with the National Renewable Energy Laboratory here in Golden, Colorado. We have a long-standing collaboration with the University of Maryland and the Coalition, and so we all three came together and pitched in our expertise to try to make this happen. To give you a little bit of background, we didn't go into this proof of concept cold. There's a long history of research collaborative research between University of Maryland, National Renewable Energy Lab, and the Eastern Transportation Coalitions. We've had past research, either demonstrations, proof of concepts, all rearward facing, all looking, can we derive accurate volume data from various types of probe data that are coming in. We can point you to studies and PowerPoints that look at Florida, Maryland, Colorado, New Hampshire, Pennsylvania, Massachusetts, Tennessee, and concurrently there's a US DOT pooled fund study that's going on that's trying to understand it fully and make sure that we apply it appropriately for AADT purposes moving forward. Again, an historical backward-facing type application. But in general, the background for this is historic volumes are viable. There's details to be worked out on how to validate and calibrate, but in general, the research shows that we can move this. And there are actually products on the marketplace to attest to this, products that are rearward looking at historic volumes. So we feel that we have that mastered. There was a discussion in the coalition of how do we bring this to operations, and to really get that benefit, we need to bring it to real time. We discussed doing another kind of rearward facing demo during the hurricane season, and then something new came on the marketplace in 2020, what we call connected vehicle data. We'd really been limited to try to apply this in real time because the data sources had not evolved to that, and this connected vehicle data through our partner Wejo was the first entry. So we tried to put this together and put together a proof of concept to see what the issues were and see if we were ready to make that jump to a real-time system. So we're calling this the Eastern Transportation Coalition Pilot Proof of Concept. Can we use connected vehicle data, which is a form of probe data, not to be confused with connected vehicle data related to DSRC. It's probe data that comes directly from original equipment manufacturers. Think of the big three or even more than that across the world. More and more of these vehicles coming right off the assembly line are embedded with the telemetry needed to bring data in mass. And that is what we are hoping to do. And we're hoping to do it within the context of the hurricane season, which is growing in importance with the global warming concerns, and seeing with those, if we could provide meaningful feedback to operators. Are people getting out of the way? Are they taking appropriate precaution? Are roads getting overloaded? So forth and so on. Things that you need to know in an operations sense to manage events like this in real time. So here are the players in the framework. The Eastern Transportation Coalition provided the overall coordination and funding. Trafax, Peter Carnes, and others associated with the validation of the vehicle probe project got involved and helped us bring the data together and process it. It was Peter, it was Kaveh, and it was Zach through all this that brought together and provided some insights on how accurate this program could be. We particularly thank all the state DOT members that participated. They're listed there. We reached out and gathered data as quickly as possible, and then we reached out and accessed your best data scientists, and Denise is going to go over that a little later. Wejo was our data partner. They provide connected vehicle data, and you'll hear from Jaap later. They brought on board Moonshatter, our analytics partner, Imar and Vonder. Shout out to them for working through this as quickly as possible and helping us achieve this. And then my lab, National Renewable Energy Lab, that are interested on this not only for the operations, but the long-term, how do we use such data for energy efficiency and sustainability. A brief overview. We use data from what we call connected vehicle data. It represents about 3% or more of all vehicle trips on the roadway, and we get data from each vehicle every 3 seconds. We reached out and we gave licenses, or basically a seat at the virtual analytics tool across all the participating states, and to a few others in the coalition to get their feedback. We attempted to estimate volumes on real time on scaling factors. I call this the algebraic approach as opposed to the calculus approach. If you look at the research in estimating volumes, there's a lot of AI and machine learning. We said let's take this a step back and see if we can just do simple linear scaling factors and see if we can make it work. And if we can do that, then it opens the line to more sophisticated tools later. The states are highlighted. These are typically the states that are impacted by hurricane events. And we look specifically at the top road classes, functional road class 1, 2, and 3. And these are, specifically defined. We used OpenStreetMaps, but they correlate well with what we're used to as far as functional road classes 1, 2, 3 from the FHWA. Our overall purpose, and this is what we hope to share and relate and conclude today, are we ready to apply what we know works as far as real-time volume estimation and apply it to a real-time data feed, and what are the issues involved? For the more technical, this is the data layout and the process flow chart. This is about the most technical it's going to get today, so let everybody know what's happening. If you start in the upper left box, you'll see data from fleet vehicles. These are actual vehicles from car manufacturers. They report back to home, and the vehicle manufacturers packages this up, sanitizes it, delivers it to Wejo. Wejo consolidates it and puts it out in real time. Note, when we say real time in this, we're talking 30 to 60 seconds from the time it leaves the vehicle to the time it's ready for applications. That's the context. There's two parts of this. There was the historic, where we looked at data from June of 2020. Kaveh is going to report on that. We used data both from Wejo as well as the state continuous counters in our focus regions to calculate uplift factors and estimate accuracy. And then we had the real-time proof of concept, which ran from September to November, where we're looking at this fire hose of data in real time, processing it in real time, and trying to estimate what the volume looks like and how we would manage it in an implemented system. We separated our goals and objectives for this proof of concept into 4, and this is how the presentation is going to be presented today. We wanted to demonstrate that real-time connected vehicle data, which is representative of about 3% of all vehicles, can be delivered and visualized in real time. We kicked the tires, but we really hadn't taken it for a test drive. This was our first test drive. To understand this fully, I'm going to turn it over to Jaap here in a few seconds, but this was a step saying, okay, we've all looked at the glossy brochures, let's put it to the use. And in short, it is, as claimed, an incredible wealth, rich data source that the states are going to begin to take advantage of. The second objective, we wanted to process the observed trips, the data coming from Wejo through an analytics system. We needed to assign them to roadway segments, obtain the counts of probes, and eventually factor them up to estimate traffic volume. That's where Moonshadow came into play. We worked with them directly on a short time frame, and were able to accomplish many of our objectives in this successfully. 3 is assess meaningful volume measures. This is, if 1 and 2 were successful, 3 was really the heart. Are we ready to jump and apply and get real-time volume ubiquitously, all time, all places across the entire roadway network? That's where Kaveh and crew Peter Carnes for coordinating, and Zach came into play to take the best look that they could to see if this is viable, and you'll hear from him. Lastly, we wanted, this was kind of our stretch goal, show that mobility patterns of people could be reflected in real time. Are people getting out of the way? This is really looking at origin and destinations. We couldn't spend a whole lot of resource on this, but have a few case studies that we can inform people. So those are our 4 goals and objectives, and we're going to step through these. Spend a little bit more time on 1 and 3 to summarize this out and then share some insights from the states. So the first one, real-time data, connected vehicle data across all states is delivered and visualized. This is a new data source that appeared on the radar in 2020, and to understand better what it is and how it differs from what we currently have, we're going to ask Jaap from Wejo to take the con and talk us through that. Jaap?
Cool. Thanks, Stan. I hope everybody can hear me okay from the other side of the pond.
Loud and clear.
Sounds good.
Okay, cool. I'll progress then. So thanks again, Stan, for the introduction. Yeah, my name is Jaap van der Hoek. I'm the Director of Solutions Engineering at Wejo. Maybe into addition what Stan said, we're actually on the market since 2019, but we're really making headway towards the end of 2019, 2020, and for us it was a great opportunity to work with the coalition and NREL in this proof of concept. Definitely we had to do some improvisation on our side to make it work in such a short time. But as you can see from these impressive pictures, when hurricanes approach and there's so much traffic and so much happening in these 6 states, it was really a cool opportunity to see if our data would work well with the Moon Shadow application in this case that we selected for this purpose, and if we could bring the objectives to life. In particular, the second volumes was, I think, a challenge because it had not been done before to try and produce these in real time. So I'm going to take you through some of the KPIs. In particular, why the connected vehicle data is so much better than other data. It's coming directly from the vehicle, as Stan already alluded to, and it doesn't have the noise that come with a lot of other sources, like mobile devices being carried around in bulk by people on trains and buses and trams and on non-roadways. So the picture from LA is showing, and where we're showing it here on the right in the picture that's playing, that you only get the vehicles that are on the road producing that data from the vehicle, where the vehicle is, the SIM card is built into the vehicle off factory, and that data is coming through in the 3-second increments and reaching us between 30 and 60 seconds, and we're ready to output it to the customer. So in this case, we were able to output our data into the Moon Shadow application, where Moon Shadow could take that data, process it, and being able to output it back to the users and giving them that overview. So some of the power of the connected vehicle data is that with the 3-second capture rate and the 30-second latency, 30 seconds to 60 seconds, it will give you that very granular, very crisp and clear breadcrumb trail of the journeys that we are tracking. And the volume is really high. So again, this picture here on the top right-hand corner is showing you that high volume, but also that high density and granularity of the data. So on average, we're tracking over 1.3 billion journeys a month, and we're tracking around 350 to 450 billion data points a month for the US. So we'll get to some KPIs for the states that we worked on the POC in a minute. Of course, also the accuracy of the data in the left bottom corner here is very good. We can identify lanes, we can identify parking spots, and with the information contained in the data, we can also identify the vehicle make and model, for instance. So in this case, we only used our real-time data to be processed by the Moon Shadow application, but there's many more events that we can glean from the data. So harsh braking, harsh acceleration, external temperature, wiper activity, fuel levels, autonomous braking, and many more events that cannot be gotten from any other device that is not directly connected to the vehicle. So for the hurricane proof of concept, yeah, there was a challenge to do the preparations in a fairly short time. So to set up a data connection, of course, work out with the Moonshot application how they were going to process our data. And if anything, we were pretty challenged by, can we generate volume estimates in near real time? And sort of the definition of the near real time was given, that's 15-minute buckets for you. And yeah, we thought it was challenging, but hopefully we're going to be able to demonstrate that it worked. So providing data for the 6 states in real time to Moonshadow was a matter of, setting up a streaming pipe and getting the data out to them. The period we worked in was September 1st to November 30th, 2020. And again, the technology that we used was the Moonshadow live traffic application fed with our data. Some of the KPIs I hope will speak because the large numbers are, I think, quite telling and compelling. We had around 2.5 billion waypoints every day and 7.5 million trips on average, with a vehicle population of around 2.5 million. So that's all on a daily basis. Peak hour vehicle update, so during normal operating hours, daytime, was around 100,000 per second, and files per hour created 40,000. So that sort of equated to 50 gigabytes of data a day. So you can imagine the data load over the 3 months period was quite heavy. We had to do some internal calibration and parameter settings to get it all right. But I think, again, given the fairly short preparation time, it was very, very quickly up and running and performing as it should, as we were able to put the vehicle to the user map around 45 seconds, and the average user map update frequency down to 30 seconds, which was well below the threshold of the average 5 minutes that we sort of set ourselves as a benchmark. So that performed really well. And again, with the vehicle update being 3 seconds, it amounted to a lot of data that we've been able to produce. So in short, the Wejo data is a true big data source. It's terabytes of data just alone for the POC, and adding to the value, that's a real-time data source within a very, very small capture rate, giving you so much data. It's over 2 million vehicles a day, 75 billion data points, over 200 billion data points during the POC. And I think for me, the real gain here was that, we tried to validate that we could show a second volume uplift in these 15-minute intervals, and hoping, I'm not giving too much away, that we succeeded in that respect. Also, we were able to provide through the Moonshot application, DB4 IoT, that real-time monitoring was possible, and also providing the data back to the coalition later on to be used as historical data, and that we complemented with the second volume data as well. So that provides also after the POC a very interesting data set to be working with. So from our perspective, we could say we've met objective 1 and 2 for sure, and I hope that Kaveh is gonna speak to the results for objective number 3. Thanks for your time, and if you have any questions, happy to answer them later on.
Thank you, Jaap.
Dan, yep, thanks.
I'm going to pause here for questions. There was one question in the chat box. I'm going to kind of some lessons learned for goal number 1. First, we took the test drive. CV data is viable in real time. Ingesting, processing, and displaying real-time connected vehicle data is no small feat. I think the whole team can attest to that. The just sheer volume was a challenge at every turn and at every task. Do note that this data was map agnostic, and we're going to get more into that later, meaning it reported pure data in latitude, longitude, geodetic format, not in a map base. That has advantages and it has disadvantages, and we'll touch on that later. But with that, Joanna, are there any questions out there concerning the nature of connected vehicle data and why it was kind of the key ingredient to make this whole proof of concept possible?
Dan,
I think there's one question in the box. I think it was Hapta asked the question about, from the states shown, which state has the most connected vehicle fleet? You partially answered that question. I'm wondering if maybe Jaap would have any idea before we go on about that.
I think from sort of top of my head, it would have been Florida with the most connected vehicles, but it's an interesting stat. I can actually have a look into that and add it to the presentation later if you want.
Jaap, I think Peter Carn actually did a response for you, and it is Florida. So yeah, you're right on.
All right, fantastic. Thanks.
Cool. We're going to have a couple representative slides of Goal 2 before we get to Kaveh. Just kind of, Jaap spoke to both Goals 1 and Goal 2. The Goal 2 specifically was, can we process this in real time to get to the information we wanted? We wanted to both visualize the data, assign it to segments, and then set it up so we could estimate volumes. That's where Moonshadow came in and used their DB4 IoT platform, ingested the data and moved it forward. One of the biggest feedbacks from many of the states was that the ability to see this data in real time, even before we process it to volumes, had good intuitive value to let them know what was going on in the network. And we're having KMJ play this video. This is the actual interface with the DB4 IoT platform from Moonshadow. And once you learn to master it, you could zoom in and take a look at real-time data coming in here. Each one of these dots is an individual vehicle, and you can see the movement of these dots. These are the updates every 3 seconds, so you can get an idea of the sense of flow, the sense of what is going on. One of the major feedbacks saying, wow, this really completes or turns the key, understanding that each one of these dots and their movements is live, meaning it's updated within 30 to 45 seconds of when it was actually collected in the field. One of the things that was noted that this may be helpful for is confirming contra flow lanes, when they're open, when they're closed, when they're in transition. Also helps understand that during a hurricane, if you want to zoom into a specific route or roadway, provides intuitive feedback. Okay. Justin, we can go ahead and close that out. And I'm going to move ahead. Specific to lessons learned, these are kind of more technical in nature. CV data is incredibly intuitive. We do have to get the volume estimates. That requires aggregation to the segment level. Conflation, which is a 4-letter word for many states, is mapping all this data to appropriate segments. This project used OpenStreetMaps. That's what OSM, because it's license free, as that base map. The message here, doing it in real time, is challenging, but it is doable. Moonshadow handled that process for us. DBIO4, though robust, I should say very robust, it's a database interface platform for if you're familiar with IoT, Internet of Things. It did require some data science skill, and one of the things we learned in this is working between bridging the language of traffic engineering and data science. We really appreciate Moonshadow for being patient and going back and forth. I think one of the things that we had to make clear is volume in a traffic engineering sense means something different than volume in a data science sense, but we worked through that. And moving into an implementation, if we were to do so, and to move it out of the realm of data scientists, we really need to work on those easy buttons and get that figured out. But that was just one of the insights there. We worked through it. Approximately 30-second measured latency. I think Jaap touched on that, 30 to 60 seconds from what's going on in the field to that rich interface that you see. To stress a little bit, the volume of data, it took, of the 3 months, it took about the first 2 months to get everything in kind of Goal 1 and Goal 2 completely stable and in place. And once we were there, we were able to take a look at some of the volume aspects of that. A lot of the attention was played on getting all the bugs worked out, but we were able to do that, and we'll give you some feedback. The next goal of the proof of concept, and that once we got 1 and 2 in place, this is really the meat of it. Can we assess meaningful volume measures in real time from the live data streams, calibrating it to know journey penetration rates and relative to nominal traffic conditions? We could no means put a complete calibrated end-to-end process in place in the short amount of time that we had, but this is where the TRAFX crew, Peter, Kaveh, and Zach came in and with the resources they had, tried to produce as much evidence as possible to see whether we could accomplish this goal 3. With that, Kaveh, the floor is yours, and why don't you talk us through what you have as far as that evidence?
Sure. Thanks, Stan. Do you guys hear me well?
Yes, loud and clear, Kaveh.
All right, very good, nice. So good afternoon, everyone, and thank you for joining. So let me go through the slides. Okay, I have the control. In the process of estimating uplift factors for this POC, we have started with accessing 1 month of Wejo connected vehicle data, as Stan mentioned, specifically June of 2020. That's the month that we use. First, we have snapped the waypoints and then conflated counter stations to the OSM network. After that, at continuous counter stations, we calculated uplift factors, and the next step was to generalize these factors to the rest of the segments in the network. So just to give you a brief, overview of what the process was like and what we went through. We performed the calculations for 3 states that, given our resources and the time that we had. We focused on Florida, North Carolina, and Virginia. In each state, we focused on top 3 functional road classes, FRC 1 to 3, basically. And images to the right of the screen show examples of each road class, so you can get a sense of what we call FRC 1, 2, or 3, based on the number of lanes, median, shoulders, and so on. Once we have started the process, soon we recognized that day of week and time of day are also important factors that need to be considered in the calculations, mainly due to the fact that traffic has a recurrent nature to it, and especially in segments with higher classification, that was more clear and more obvious. We targeted 15-minute time intervals in all 7 days of the week. For each day, we have 96 time intervals to calculate. On input data, I just want to briefly note that counts at continuous counter stations are typically aggregated on an hourly basis. For us to get to the 15-minute counts, we had to make the assumption that traffic is uniformly distributed in the hour. So that was one of the assumptions that we made early on. Then some continuous counter stations do not report directional counts. In those cases, we made a 50-50 split assumption. In this POC, obviously, moving forward, we can use more sophisticated means of splitting the counts. And obviously, snapping and conflation of this large amount of data, as Stan also mentioned, needed a lot of work. The process can be obviously improved, and in the future, we are working on streamlining it for implementation. Also, potentially in some geographies, connected vehicle data and counts may be reported in different time zones. That's just a note here. In general, obviously, we didn't have to deal with it in the 3 states that we focused on, Florida, North Carolina, and Virginia. But that's just a note that this may happen and has to be taken care of in the future. This slide gives you a summary of the statistics on the number of FRC Road 1 to 3 OSM segments in each of the states that we did our uplift factor calculations in. And also it gives you an idea of the number of continuous counter stations that were actually used in our calculations in the POC. So as you see, there's a mix of FRC 1, 2, 3 in all the 3 different states, and you see the numbers in terms of the total miles covered and the number of of data that were used. Here's an example of the kind of results we got. This graph shows penetration rates. Alternatively, you call it uplift factor, or you can think of it as an inverse multiplier that were calculated for a single FRC1 segment in Florida. The x-axis here is the hour of the day, and each colored line in the graph indicates a different day of the week. So we indicated, Sunday, Monday, and then so on with different colors. It's interesting, and probably the main finding here is that, as you can see, overnight hours, typically lower volume hours, they show larger variations in the penetration rate. But during the day hours, let's say from 5 a.m. to 10 p.m., penetration rates across different days and also within each day is fairly consistent, and shows much smaller fluctuations relative to low volume hours. This is a key finding, and it was important for us because it indicates that connected vehicle data relative to actual counts, actual traffic counts, is stable in times that matter most to most operations applications. So, this is, as I said, is an exciting piece of finding for us, and indicates our approach is viable to provide meaningful volumes in real time. We can do this simply by multiplying the unique number of probes in each time interval by a factor and get a good estimate of the volume. This is another example, again in Florida, but this time on a lower level road class. This is FRC3 segment. Again, results are consistent with our previous findings, and as you see, it shows the same kind of stability during the core hours of the day, and it was again a reinforcement of our earlier finding that even in FRC3 segments, we are seeing the same stability in terms of the relative number of probes to the actual traffic. This is the slide that pretty much summarizes all the findings in this case for Florida, but for other two states, North Carolina and Virginia, pretty much we had the same kind of results. Interestingly, this shows that in different road classes and different days of the week, we're dealing with a very consistent ratio of probes to actual traffic counts. Also note that this is a box whisker plot, so you can see the interquartile range very clearly, for each of the road classes in each day. The largest interquartile range is 4% in this case, which is very interesting. And by all measures, it indicates that the estimates are very tight, and we can use this to reasonably come up with volume estimates that are fairly accurate, and for most applications could be relied upon. In summary, the findings and lessons learned in this POC are given here. I already touched upon them. I'm not going to go through the whole list. But if you have any questions or need more details about this, please let me know. I can get back to it and provide more details. This slide, basically, is my attempt to answer the question that Stan was talking about before I started speaking. The goal number 3. So we need to take a step back and think about what we saw in this POC and what we found, and the other approaches that we have attempted in the past. So of course we could approach this problem using more sophisticated methods, as Stan mentioned, machine learning and AI. We've done it in the past, but the reality is that our findings are indicating that this may not be necessary at all. The consistency and the stability in the probe data is there, and we can leverage it and take advantage of it. This POC showed us that uplift factors seem to be adequate for what we have in mind and our targets. And also this provides a more intuitive and scalable method for real-time volume estimation, which is something that that helps us in this process. So based on these findings, my answer to that question to Stan is a resounding yes, and I'd like to indicate that I'm happy with what I saw, and it's a good indication that we can use this method in the future to estimate good real-time and accurate volumes for use of the community moving forward. And with that, I'd like to give it back to you. And if there's any question, I'd be happy to answer.
Thank you, Kaveh. I'm going to leave it on this. I think this summary slide is probably the most critical one of the entire presentation because we wanted to get this question answered, and I sure appreciate Kaveh's and team's attempt. I respect their data statistics and processing about more than anyone else, and so we had a lot of back and forth. What does this data mean? What does this data mean? What do the statistics point toward? And we spent a lot of time getting the wording on this slide correctly and kind of put Kaveh on the spot, saying, Kaveh, you're Spock. Should we invest in this moving forward? Is it ready and mature? So we feel quite confident in that last overall bullet that there's enough evidence here that we could build a viable real-time volume estimate system at this scale. There's a lot of questions coming in. We tried to answer them. One question was on OSM segments. They tend to be to break and access 1 to 2 miles. Where did the calibration data come from? That came from the continuous count stations. Peter Carnes reached out to the participating states and tried to get the corresponding data from all the continuous count stations for that state in June of 2020. Sean, did you quantify workable volume estimates in terms of calculated error rates via cross-validation? In this case, no, the cross-validation comes from machine learning and AI. We use the more traditional statistics, looking at regression analysis and pure proportions. I'd invite you, Sean, to take that up with Kaveh. I know they're going to move this towards a more in-depth evaluation that gets all the statistical summaries that all you data scientists will want to see. So we tried to boil it up to the very top here and say, was there enough evidence here that we could do this in real time? Okay. I want to address Autumn's question on segments without continuous count stations. Did you eliminate the segment or apply the conflation factor consistently? That's a good lead-in into moving forward. Everything that you saw from Kaveh was based on calibration data from continuous count stations. Our goal was to turn that around and hand a table off to Moonshadow to say, here are the uplift factors that you would need to apply by state, by road type, by time of day, and by time of week. We never got to that point of creating that full table, but we got to the point of assessing whether that table could be created and could be consistent enough to be workable. Moonshadow created that actual table in their software, but I don't believe we ever got to the handoff point. They used a straight uplift factor of 3% based on some preliminary estimates. Matt, boy, the questions are coming in here quickly. I'll try to address this. I think it's good to pause because this is the meat of the presentation. Did you have any randomly large volume days from any of the states? Basically, did we have a good example of people evacuating an area, and did the volume estimates hold? Address that in two parts. Most of the anomalies that we saw in the calibration of what Kaveh looked at were hourly, overnight hourly, particularly when the volumes were low. And I invite Kaveh, if he wants to comment on that, he can. The other one is in the next, we looked at anomalies. Can we see changes in behavior relative to hurricanes? Thankfully, during this period, there was no direct hurricane hit. There was a significant tropical storm in early September, and we worked directly with Moonshadow and Vonder to do some kind of ad hoc analysis if we could see that. I'll share that in a few slides. I'm seeing Josh Rolls using some cross-validation on the count sites. Yes, we could do that. Let's take that up with Kaveh. By cross-validation, it's a process where we develop a methodology based on a portion of the calibration data, say 80% of it, and then apply it to the remaining 20% to see how accurate it is. So Josh and Sean, I'd encourage you, let's take up that conversation afterwards and discuss it with Kaveh and see if we could do that quickly with the effort that we currently have in-house. That would be good. I'll pause a couple more before moving on. Another one came in. Thanks, Trish. Trish says we're going to rename the bleeding edge to the exciting edge. I agree with that. This I think is some of the most interesting work going on. It may not be, as I said, the calculus version. It may be the algebra version to begin with, but it is showing what is possible and what we can build. Can we clarify similarities, differences between this work with Wejo to the VTM project? Kaveh is typing a response. I hope you can. I'll provide some top-level responses and invite anyone else from the team if they have to cut in. The biggest difference is getting it to real time and the quantity of data. I think everyone who participated in this, we understood that this would come fast and furious, but our expectations of fast and furious versus what actually came was an order of magnitude difference across the entire team. So we had to learn to adjust and adjust quickly, and we were able to do that. The other is under that, the previous volume turning movement research work over the last 3 to 5 years was always in a retrospective sense. So we had the luxury of applying any and every data methodology we could, and the team resorted to machine learning, tree learning methodologies, as well as AI to squeeze every ounce of accuracy out of it that was possible. Going into this, we knew we didn't have the resources in either funding or time to go to that level of detail, so we stepped back and did a much more basic approach of estimating these scaling factors. And if the scaling factors worked, we had confidence that if we had enough time and resources, we could bring in more sophisticated methods. And I think we all are seeing the results, feel that we've attained that. So, good. Josh, Kaveh answered it there. Taking a look at those interquartile means, those statistical rollouts, and how consistent they were from day to day and hour to hour gave us confidence that we could bring meaningful information from this. If there's no more questions, I'm going to move on. We're going to share more insights and more state feedback. I'm going to start with proof of concept 4. The whole concept, can we show that mobility patterns of people change, not just volume counts on a roadway, but are they getting out of the way of the hurricane? Are they doing things differently? As I said, this was kind of our reach goal. Goals 1 through 3, absorb 95% of our resource. So when we got to goal 4, we were kind of running on empty, but we worked with Moonshadow specifically. There was a glancing blow or a tropical storm that came on to Alabama at the early part of September, so we reached back and got some information from there. Through this all, just these are just observations that we were able to glean, and unfortunately I don't have good graphics to back this up, but we're working on that if we get some more time. We could see consistent origin destinations patterns that were repeatable day to day. just as we could see repeatable volumes, things like that. And if that were so, we hypothesized that during the hurricane, the OD pattern should reveal people getting out of the way or sheltering in place. And if there would have been a direct hurricane hit, we would have probably put more emphasis on this, but there was not during this. Note real time with respect to these mobility patterns are not measured in second to second or 30 seconds or 60 seconds, but rather in the daily diurnal patterns. Did people go to work like they normally did, or did they do something else? Typically measured hourly patterns, so a little bit different concepts. The case studies we conducted with Moonshadow revealed observable changes in roadway use during onset of a September tropical storm. This was on to my non-coastal origins are going to be revealed here. The islands that typically border, I believe it was Alabama to the south during the tropical storms, measuring the roadway volumes across the causeways were noticeably different during the tropical storm period than they were during the normal periods. And we also did something else. We said we hypothesized that visitations to stores like Lowe's and Home Depot, home improvement stores to get plywood and other supplies would escalate during hurricane onset, and we definitely saw that during the tropical storm in September. So those were some just top-level anecdotal evidence. We didn't have the time to dive into this, but overall, the real-time OD behavior is a new area that has typically almost been 100% backward-looking. So it's an uncharted field to get effective visualizations and information out there for states. So it's a great opportunity to move the needle forward. At this point, after we've talked through the 4 objectives, I'm going to turn it back over to Denise to introduce our state experts that had eyes on this the entire time and get some salient feedback from them.
Thanks, Dan. I have a couple slides before I turn this over to Simona, but I think one of the pieces of information that we did a little different with this proof of concept was that since we had such a short amount of time, typically you have a longer-term research project. You know, your team goes in, does research, comes back to a steering committee and holds a webinar and gives you the updates on what's been done. Because we were more compressed, we said let's put some of this feedback and direct feedback and development in the hands of the states and their users. So we identified some what we call power users or subject matter experts from the participating states. And we asked them, we gave them a period of time of access to the DB4 IoT platform, the visualization platform, and interface with it, look at it, provide us feedback. And knowing what you've heard about the challenge of getting things up and running and getting it all working, they were good because they provided us some really helpful feedback. We gave 21 licenses, we purchased, I should say, through the process, 21 licenses. 3 of these licenses went to each state for 3 users. And I have to say that one of the things we did miss, Stan, is that we didn't put a picture of Wander on our technical team. And so my shout out to Wander. He was our training person. He held training sessions, specific one-on-one training sessions with these users to walk through how this interface platform was going to work. So he was amazing. And so my shout out to Wander is that next time I'm sure you will get a slide with just your picture on it. But after the training, the key piece to know is that sometimes the users came back to us and said, I'm not the guy, I'm not the girl to be doing this. Let me hand this off to somebody else. And so we ended up transferring some of the licenses, which was a very important takeaway for us. And then those folks were the ones that attended, again, one-on-one training. These are some of the folks that we talked about from the states. The folks that are listed in red were really identified as some of our power users. You know, shout out to Alex or Raj or Brad or Kelly, Simona, Alex, or Dr. Srinivas. They really got into the depth of the platform and started to look at what worked and what didn't work. So I'm going to turn this over to Simona. So she is from VDOT. She is one of the data scientists there. I asked her to come in and she providing some great slides on her perspective, what she felt worked, some challenges. And so with that being said, Simona, I'm going to turn this over to you. Are you there?
Yeah. Thank you, Denise. Can you hear me?
Yep.
Hello. Okay. Thank you very much, Denise. So good afternoon, everybody. My name is Simona Bobiciano. I'm with the Virginia Department of Transportation, and VDOT has participated in this pilot project, and I would like to share with you a few of the lessons we have learned from this pilot. So first of all, I'd like to just mention that in a nutshell, we are very impressed with the data size, with the data freshness, and with the spatial coverage that the data was provided to us. This is the connected vehicle volume data complements currently available volume data in VDOT. So we currently collect volumes with continuous count stations, with temporary coverage counts, with Bluetooth or cell phone splitters, but these are difficult to deploy and they don't scale at all well for large geographical areas. So this has actually this would be able to meet a lot of our needs in that area. And with respect with the freshness of the data, we have seen that, like in my experience, there's a lag of about, let's say, a couple of minutes, sometimes a minute, around that time. So it is really, we really don't have a volume to provide this type of freshness. And this is very variable for TOC floor operations as well as for weather events or hurricane evacuation operations. It can help us understand which are our more frequently or less frequently used roads and help us see the compliance with the designated evacuation routes in case of a hurricane event. And the last bullet, Northern Virginia, our most urbanized region from the state, is part of the Washington, D.C. metropolitan area, from which the District of Columbia, as well as parts of Maryland, are part of, and a traffic event in one of those most likely can influence traffic in Virginia. And this way, with this type of ubiquitously available data, we can track down what's going on here. Next slide, please, Denise. Thank you. So some of the challenges that we have noticed that could potentially be improved on a more production or larger scale of deployment of this pilot are scaling journeys to volumes, and Kaveh and other speakers have talked to this topic earlier in the webinar. To be able to build trust in the this trip and volume data at the DOT level, we would need to, I personally think we would need to set up a systematic and continuous validation program, as well as a system for customizing the uplifting factors, maybe even the methodology for converting journey IDs to volumes. Some of the only vehicles, newer vehicles equipped with this connected vehicle technology can be probed in this system. So there's this inherent bias towards newer vehicles. And it could also be that there's some kind of implicit bias towards more economically prosperous segments of the population who can actually afford to buy these new vehicles. And the latitude and longitude information that comes with the data is oftentimes sufficient to identify one location or up to a particular address. So concerns around tracking individual people's behavior and privacy are raised, and they have to be carefully thought of. Other issues, in some cases we've seen very high speeds, not sure where this comes from. There's some cases where there's data updates. So for example, we've seen cases where a vehicle was tracked and then kind of disappeared for some number of minutes and reappeared 2 or 3 miles down the road on the same road. So there was a period where there was a lack in coverage, a gap in coverage. And we are very happy to see the use of the heading data element because just the lat longs is not sufficient in all cases to identify the direction of the road, especially for roads that are not separated by some median in the middle. So next slide, please, Denise. Thank you. So this matrix represents origin destination matrix for 1 week worth of data for Virginia. I have downloaded this data that I have to thank Wonder for providing to us. So he provided 1 week of historical data, and I have used the county attributes of the origin and destination of trips. I mapped the counties to VDOT districts, and there is a map for your information in the upper left corner. And then created this matrix. And I would like to comment that these numbers kind of make sense. So on the diagonal are the highest numbers. So it means that the highest number of trips were taken within one district. And also the farther away two districts were, the fewer trips were recorded for between those two destinations. This is especially visible for the Bristol district, which is in the southwest corner of the state, which has the fewest trips between itself and the rest of the district. Next slide, please. Thank you, Denise. So in conjunction with that user customized created image, there are some visualizations that I have taken from the DB for IoT Moonshadow tool. The one on the left with the dark background represents a visualization of volumes on a zoomed in area in Northern Virginia. The road that is north-south, and it's mostly pink, is the Capital Beltway, I-495, and the one that also has parts in pink is I-66, goes east-west. The more pink the road is, the higher the volumes. The roads that are in blue are with lower volumes, and the other ones were outside of the study area. So only FRC 1, 2, and 3 were part of this pilot. So I have noted here that in the tool itself, I was happy to see that at a glance you could easily discern between the two directions of travel. In this particular zoomed picture is being minimized, and this distinction of the directions of travel is not that clear, but it does exist in the tool. And on the second one with a white background, we have selected this little area on US 50, which is the road with in the lime green colors, and it also cuts out in the rectangle little other small roads. And the interesting thing to see is in the chart where on the y-axis is the number of trips that's plotted against the heading on the x-axis. You see those two tall bars. Those are the headings for the vehicles that would travel along US 50, about 180 degrees from each other, and the little bars are headings from the trips from the other roads that are in orange or red here, so much fewer than the rest. So all this is what we would expect. Very happy to see that. Very nice visualization. Thank you.
Thank you, Simona. That was great. I think the comment you made about the conflation, or excuse me, the validation is really good, and we're glad to hear you had some great comments to add. These are a couple more slides as far as state feedback. Brad Mann couldn't be on the call today, but he was kind enough also to provide us with a couple of screenshots as he was poking his way through this platform and looking at this data. And two of them that he brought up that he thought were very helpful was that this type of query that he could generate on the screen shows how the color gradient can be changed for roadways, like during the AM rush, which is what he did here. I do know he did make a comment, too, about having to export data and exporting it down. Comments about into an Excel spreadsheet would be helpful to do that. So he was able to provide some useful feedback to IMAR and his group. This is, for example, another screenshot from Georgia DOT talking about his querying of speeds set up for, I think it's I-75 from the Midtown to I-285, for those of you that might know where that is. But and his note, what he really enjoyed was this number of events up in the top. It displayed in the white box, the upper right. So again, great feedback to help in the development of a platform directly from our state. So these are some comments. We captured a bunch of data. We actually held some interviews with some of the users. Again, Simona mentioned that from Virginia, they're interested in increased coverage for volume estimates, so this looked like it had great potential. One of the recommendations that they made, and she made for potential performance enhancement, was maybe to create smaller regions, because we're hearing about how the data, the bulk of the data was so great. Maybe you take a region and extend the boundaries around your state borders, and maybe look at that, creating a smaller region. That was an idea that came forward. In North Carolina, one of the comments was the ability to capture the OD patterns caught their attention, and it was a wonderful source in tracking OD patterns or potential changes in traffic volumes. Florida had an interesting take on that, and as Dan mentioned earlier, their class, where data science meets transportation and engineering, is Raj was very keen on the fact that the visualization tool was not necessarily intuitive for transportation, and that's where we needed to work on and get better at. And then in Georgia, Tom McQueen, who was part of their planning group, had talked about the benefit of the data, that it gives them a different lens to look at other than just OD data. So the little chart you see on the bottom, this is a sample that was provided to me from Kelly Wells in North Carolina. She kind of calls it, I agree, the Holy Grail, is that if down the road you're able to look at and provide a chart of the number of volumes of cars that have passed through a location over a period of time when you're in a hurricane evacuation, that's a great briefing, a great piece of information to provide at a briefing. So this is, I think, the ultimate goal that we eventually want to work towards, particularly when it comes to hurricanes. So, state feedback summary, real-time display of connected vehicle data is incredibly intuitive. It does confirm conscious flow incidents, as Stan and Simona mentioned earlier. Platform was initially, it was glitchy at first. We won't lie about that, but we did stabilize it, and at the end, it really was performing well. Our volume display, it only provided probe counts till November, so and we had to deal with a specialized query. Again, lessons learned as we move forward. Visually, the density of the vehicles reinforced the ability to provide volumes. It really did. And the demo provided ample evidence that real-time volumes are really within our reach. So, and again, you're hearing this, I think, consistently, the data requires specialized resources to consume it. So I think we were all on the same page, and all the states were on the same page with that type of feedback. So with that being said, I'm going to turn this back to Stan to finish up with lessons learned and some summary findings. Stan?
Thank you, Denise. We're on the home stretch here. Just some closing comments, then we'll stick around to take any questions. The whole purpose of this is truly a proof of concept, trying to put out there the question. It looks like the data assets are in place. It looks like the technology in place. Should we move forward and attempt a real-time system? These are the overall takeaways. This connected vehicle data is viable now and will only grow in size and velocity and variety and everything else like this. We really appreciate our project partner, Wejo, and their analytics partner, Moonshadow, to prove this out in objectives 1 and 2. Managing connected vehicle data at scale is challenging for industry, but doable. And I said for industry, it wasn't just UMD and our team. It was Moonshadow, it was Wejo, it was everyone saying, okay, we keep talking about this massive data set at scale, and we put it to the test, and we had to work out a few kinks. But I just tell people, don't underestimate that challenge going into it. It is manageable, but it does take special attention. The visualization of the dots moving brings intuitive value, and I want to differentiate. I mean, Florida says it's not intuitive. It's not intuitive for volume measures. It's not intuitive for anything else, but to give you feedback of seeing actual vehicles moving on the screen gives you an idea. Hey, that road is open. Hey, that we're using the contraflow lane, things like that. We really have to snap this to segments and do our traffic engineering on it appropriately to bring volumes. But that fourth bullet is what we wanted to get at and make a determination. And we think we've presented enough evidence that real-time volume estimates from connected vehicle data appears viable for implementation. I should reread that for emphasis, but I bolded it for emphasis. This is what we wanted to get to. I think we have enough evidence here that we could step out perhaps at the end of, even in 2021, and start making progress towards that end. The proof of concept provided valuable insight into what the specifications for an operational system would be in terms of use and functionality. That was very important. You never know what you don't know. The bridge, the language between traffic and information technology. I wanted to bring this up saying if you wade into this world, you're going to have top-notch IT staff to handle the volume of the big data, and getting that bridge and understanding between the two groups are going to be necessary to get to those easy buttons. I think that was highlighted, at least for me, saying, hey, don't underestimate either of them. And we're blazing new grounds to visualize real-time volume in O&D in a rich area for the coalition to move forward and get good tools out there and hopefully lead the industry moving forward. My last slide are next steps. I don't want to commit the coalition to anything, but based on the CV data, we think it's possible. As Denise shared, the Eastern Transportation Coalition is moving forward with the procurement of its traffic data marketplace and connected vehicle data as an element, so it sets us up to put one asset in place to move forward. We hope, and we're working towards, that this proof of concept will result in a draft framework, specifications, and approach for an implementation. By implementation in real time, not a proof of concept, but a system that states can begin to rely upon for their operations, for their hurricane situations, for any other system like that. And we hope to move that forward in discussion, possibly with a program in this year. We're forming a coalition committee for guidance, oversight, and vision. This may be an ad hoc committee right now. I hope I don't overcommit the coalition towards that, towards a traffic volume project to move forward. Expect additional details or information the second or third quarter of this year as we finish up this proof of concept and have to do some other things until we can put together a more formal approach to what we foresee as a coalition traffic project. With that, I believe that is everything. I see some questions in the chat box. I know all the speakers are going to hang on until at least half past the hour or until the questions expire. I'm glad to talk about that.
Dan, thank you. Lindsay had a comment in the chat box from Rhode Island about OD data. And they have travel demand models of one kind or another for air quality purposes. So I think she was wondering, as we become more mature, could this help avoid wheel spinning? So Jaap,
yes,
I thought that. Go ahead.
I saw the note says, as this becomes more mature, integrating the data structures of the regional model TAZs may help avoid wheel spinning. I fully agree. This data comes in with some built-in spatial aggregations, and I believe zip code level and county level is one of them. Getting that data married as quickly as possible to spatial aggregations of value to the DOTs and MPOs will be a value add. Well, we thank everybody for joining. I hope we provided an adequate overview of this proof of concept and enough information to get people excited that the data world continues to raise ahead, and we want to leverage it as much as possible for the coalition and for transportation management.
And Stan, I think on behalf of the coalition, I'd like to thank the entire team, because as you mentioned, many times research takes 1 year, 2 years, 3 years to do, and we did this in a 3-month period of time. In operations world, for those of you on the phone, in operations, not a big deal, but for many times research and planning, it is a big deal to get that amount of data done. So I do need to thank everybody who was involved with this, because you really pulled it out in 3 months. So I thank you all.
Note Trish's comment in the chat box. Cool. Trish's comment says, we will push this forward to the volume holy grail. Thanks for that commitment, Trish. Autumn, are there applications to CV data beyond volumes in O&D? Oh, absolutely. We don't have time to go into that, but Autumn, let's follow up. There's several on this not only presenters, but people listening that are diving into the uses of the CV data and could share a few of them with you. But very excited that it's opening up efficiencies in assessing traffic operations management, signal timing, everything that we were hoping for and we're now seeing come online.
Awesome. All right.
Speaking to the rapidity, sometimes I think we should set limits saying what's the best you can do in 3 months and then with this budget and get out of the way. that's what this project felt like, and I think it had good results. So thanks everyone. Thanks Denise. Please follow up with email if you have additional questions. We'd love to interact.
There you go. There's Wander. Bye. Thank you, Joanna. Bye. Thanks, everybody.
Bye. Thank you.